I talked in the last video about some of the early understandings of how levels of certain molecules in the air, like carbon dioxide, are expected to affect average temperatures. In this video, we'll take a look at examples of data related to measuring the levels of carbon dioxide, both now and in the past. Sometimes, some of the best science is actually pretty simple. In 1958, Charles Keeling decided to just start measuring the amount of carbon dioxide in the atmosphere. He picked Mauna Loa in Hawaii as the spot to take measurements, largely because it was remote, and that way measurements were least likely to be impacted by local factors and hopefully best able to reflect amounts of carbon dioxide in the broader atmosphere. He set up an instrument that measured and recorded carbon dioxide, just like a thermometer measures temperature, and he measured it for a long time. Starting in 1958, several measurements every hour, every day, and they continue today. At this point, over 60 years of continuous measurements. The dataset is updated regularly and is available at a link in the comments. Here, I'll plot the average monthly values of carbon dioxide, starting with 1958 on the left and moving to the most recent measurements on the right. The points will show the average monthly values. Here are the measurements for 1958, then for each month in 1959, then the 1960s, the 70s, the 80s, the 90s, and up through today. Now, two things jump out here. First is the repeated up and down pattern that happens each year. Lower carbon dioxide in the atmosphere in the spring and summer months, and higher in the winter months. This is expected. It's a reflection of photosynthesis. Think more leaves on trees in the spring and summer, which pull carbon dioxide out of the air, less in the winter when those leaves break down and that carbon goes back into the air. Second, though, and more importantly, is of course the overall upward trend for the time period that's covered here. Of course, this specific data set only gives measurements since 1958. What if we want to know about carbon dioxide levels farther back in time? Here, I've redrawn the plot and simply extended the bottom, or the x-axis, which before covered just the years 1958 to today, but now it goes all the way back to the year 1 AD. Now, the data here are exactly the same. It might look like they go up faster, but that's just because the points have been squeezed together. Again, the data haven't changed. It's a good example of the importance of thinking about the absolute values represented on a plot versus just a shape of, say, lines or a series of points, as shapes and initial appearances can change on any plot with simple acts like, for example, zooming in or out like we've done here. Regardless, figuring out what levels of carbon dioxide might have looked like across this kind of time range requires a different approach, since nobody was taking direct measurements in the distant past. One creative method to get at this involves using ice cores. In certain places that stay cold, like the polar regions, ice accumulates in layers over long periods of time, one layer on top of the next. A little bit like tree rings, but of course, unlike tree rings, the older layers of ice are farther down and more recent layers are closer to the surface. Those layers of ice can trap samples of the air from a given time in small bubbles inside the ice, which over time get buried deeper and deeper by later layers of snow and ice. Drilling down to remove a core from the ice can allow researchers to obtain samples of the air or atmosphere from long ago. If you want to see more on how this works, I've added a link to a video in the comments. We'll take a look at CO2 data from two cores. The first is the dataset core from Antarctica. Samples from this specific core go back nearly 2,000 years and extend up through the late 19th century. The measurements across that period look like this, fairly consistent over that time period and averaging in the range of around 275 to 280 parts per million. Now we'll add data from a second core, the DE08 core, which represents a slightly different time period that fills in the remaining gap between the Keeling data and the first core we looked at. This set of data is useful for a couple reasons. First, I'll zoom in on the years 1700 to the present. Not only does this second core help fill in that gap, but it also offers some independent replication of values in both of the other data sets. Replication is arguably the most important characteristic of good science, and this data set gives values very consistent with those in each of the other two. One of which, the Keeling data, was collected by a different group of scientists using a completely different approach. Direct measurements of the atmospheric CO2 in real time versus measurements from these ice cores. The takeaway from these data is that levels of CO2 seem to have remained relatively constant, around say 280 parts per million, up through the mid to late 19th century, when they start to creep up. And since then, they appear to have continued to rise through today, where we currently have levels comfortably over 400 parts per million. In the previous video, we looked at some of the work that made predictions about what effect changing levels of molecules like CO2 might have on average temperatures. And here, we have some data that support the idea that CO2 has been increasing in the atmosphere for something on the order of the past 100 years or so. So, given this pattern, have the data on temperature actually been consistent with some of those earlier predictions? We'll take a look at that in the next video.